Hi everybody, welcome to another video in Calculus 1, section 7.2. In this section, we study about the logarithmic and exponential function. And of course, the calculus aspect to it, meaning the derivative and exponential of this natural log function and exponential function. All right. So the way to approach this, there are two approaches to this. One, we can start with the exponential function, and then we have the natural log. This book, they go with the natural log first, and then they go to exponential function. Notice that the exponential function, the natural exponential function and the natural log, they are inverse of each other, meaning that if we have y equal to e to the x, that is equivalent to sin x is equal to ln of y. Or we have the ln of e to the x is equal to x. That is the properties of inverse function, or definition of inverse function, or e to the ln of x is equal to x. Yes. So once again, the natural logarithmic function and the exponential natural exponential function are inverse of each other. All right, so we're going to use that later. But now, the way, like I said, the book approach it, they define the natural log as the integral from 1 to t of 1 over t. Right. The bad thing is using this definition to prove this is a little bit difficult. It's not totally difficult, but I'm not going to prove that because these properties we have in quotient algebra or with calculus already. Right, but right, so as first of all, we graph 1 over t, look like this, and if we define the net area as that function, then we have the natural log of x. It could be, t doesn't have to be, I'm sorry, there's a typo here, there should be x here. X could be less than 1, could be more than 1, so, but it have to be positive, because the function here approaching to the vertical asymptote, so x cannot be negative over there, because 1 over x on this side, and the other side is over here, but we're not focused on that. X only positive, so when even positive, the area from 1 to x or from x to 1, x could still be between 0 and 1. That's why I try to say x can still be between 0 and 1, but we still have the net area. Right? Notice the net area from x to 1 is opposite from 1 to x, but by this definition it is 1 to x. Here we write from x to 1, so that's why if it is ln of x, it's going to be positive if x greater than 1 is equal to 0, if x equal to 1, because when x equal to 1, we don't have any area, we go from 1 to 1, so that's just a vertical line. And it is negative if x is between 0 and 1, and x cannot be negative for the natural log, and we cannot put in 0 either, so there's no equal sign here, just between 0 and x, 0 and 1. So those are the values for the natural log function. Right. Next, we have these properties. Even though in terms of calculus, derivative and integral, it might not be as important as what we have in quotient algebra or with calculus, but knowing this will help us a lot. We will see ln of a product, we can turn that into a sum ln of a quotient, turn that into a difference. And if we have the power, we can always take the power outside as a coefficient. So these three properties of the natural log is very helpful when we take derivative. It will save us a lot of time. Right. And finally, the properties of the natural log, the domain from 0 to infinity, because we said x cannot be negative, and the range could be negative infinity to infinity, and the graph of natural log function like that. Right, because we have all the properties there. Right, so properties of the log obviously important, but the most important that we study about this is, of course, is the derivative and the integral. Right. So derivative of absolute value of x is 1 over x. The reason we put absolute value of x there because x could be negative. If x is negative, then ln of x is undefined. So we can put absolute values there and it's still just 1 over x. But we still don't want to divide by 0. So that's why x is not equal to 0. So the derivative of ln, whether we have absolute value or not, is still just 1 over x. And x not equal to 0. Of course, we assume that inside the log have to be positive. And of course, antiderivative of 1 over x is integral of ln of absolute value of x plus c. So derivative and then antiderivative, then plus c. Right. Now, like I said, the most important, what we focus in this section, the most is of course just how do we find derivative and integral of log, the natural log, and the exponential function. Right. So just look at the first one. Remember, derivative of the log is 1 over the reciprocal function. Right. So let's look at the first example. We have log ln of 4x. So the derivative using the chain rule, ln of something is the reciprocal. So just have 1 over the parentheses, and then chain rule says multiply by the derivative of the parentheses, regardless of what inside the ln, what is the argument of the ln. So it just happened to be 4x. Derivative of 4x is 4. You can multiply that to the top. 4 and 4 cancel out, equal to 1 over x. Right, so it's not that bad. Derivative of natural log is the reciprocal function. Right, it's not that bad, definitely, but it can get even better. Now, notice that we can use these properties, which I write again in this form. I think is better. Ln product is the sum of the ln's. Right. So we write the function y equal to ln of 4x. It is the product, isn't it? So we can split ln of 4 plus ln of x. And then we check the derivative. It should be easy. Derivative of ln of 4. ln of 4 is the constant. Derivative of a constant, 0. We have just derivative of ln of 4 is 0. Derivative of ln of x is 1 over x. So we just have 1 over x. Yeah. So knowing these properties will save us. We don't even need the chain rule if we know those properties. Right. Next, y equal to ln of 2x squared plus 5. Of course, we know the properties. They can be for a product, for a quotient, and a power. In here, this is a sum, so we cannot do anything with this. Just have to use the chain rule here. So this is, we have only one option here. That is the chain rule. So the derivative of that, reciprocal function 1 over, and then derivative of the parentheses regardless of what inside of the ln. It just happened to be 3x squared plus 5. And derivative of 3x squared plus 5 is 6x. And I can multiply it on the top, and that's what we have. Right, so yeah, just like that. Derivative of ln is the reciprocal function. Right, more example. Right, derivative of x times ln of x. Certainly we know derivative of x, we know derivative of ln of x. Here we have a product. So we just use the product rule here, right? So u equal to x, v equal to ln of x, u prime is equal to 1, v prime 1 over x. And then just the product rule. Right? Product rule. Just right. U prime v plus uv prime. X and x cancel out to just 1. Right. Yeah. We might go back to this later. Right, now let's just go to the derivative of this. I'm going to do it the long way first, and then I'll go back. And we can go back and do this because we don't have much space here. Right, the long way. Not the wrong way, but it's just long. This, I can rewrite that as x squared plus 7 to the 1/2 power, right? Now, this is the wrong way. You can put a bracket here. And derivative, of course, reciprocal function 1 over the bracket. And then derivative of the bracket. Just happen to be x squared plus 7 to the 1/2. Oh, sorry, there's no derivative here. So we just have 1 over x squared plus 7 to the 1/2. Now the derivative of this, which is another chain rule, put the parentheses, there will be 1/2, parentheses, to negative 1/2, original power minus 1, right? And then derivative of inside the parentheses. The parentheses is x squared plus 7. Yeah, if I write like this, it will not fit in that space. So there's a better way to do this, but this certainly works. So let's just clean up. I put the 1/2 in front. X squared plus 7 to the 1/2. Now, this one has to the negative 1/2. If I move to the bottom, that becomes positive. Just put 1 on the top to have the fraction. And then derivative of this, that gives us 2x. Here we can cancel out the 2 on the top, the 2 at the bottom. So we will have an x on the top. X squared plus 7 to the 1/2, x squared plus 7 to the 1/2. When we multiply two things with the same basis, combine the exponent. 1/2 plus 1/2 is 1. So x over x squared plus 7. Yeah, that is the long way to do it. Certainly works. I'll just apply the chain rule 2 times. Certainly works. Like that. Just going to put that here. Okay. Now, we're going to do that differently. Better way. Now, of course, first, we still write this as ln of x squared plus 7 to the 1/2. Because usually when we take derivative, we write as a power is better than in the radical or square root form. Now the properties that we use is these properties. We can take the exponent outside. So let me write ln of something to the p power. We can take the p outside. And now we have that. So in which case, we can take the 1/2 power outside. And doing that, the chain rule will be a lot easier to do. We only need to do one chain rule. Yeah. So we still have ln of that bracket. Now we can take derivative. Derivative of ln, of course, is the reciprocal function. We still have 1/2 regardless. Ln, derivative of ln is 1 over that. And then chain rule say derivative of whatever the argument of the log. So I have x squared plus 7. And that gives us 1/2 1 over x squared plus 7. Derivative of this is 2x. Right, we can put 2x on the top, with the 2 on the top, cancel with the 2 at the bottom, and we have 1x on the top, and x squared plus 7 at the bottom. Right? Yeah. So, every time we take the derivative of ln, it is 1 over that, which is easy. But take advantage of properties of the log. If there's a power, we can take it outside. If there is a product, try to break it up. And derivative of each individual one is a lot easier to do than the big log. So that is derivative. The derivative of the log is the reciprocal function. So that's the first rule we know. Now, next, the second part of it is the integral. Of course, the antiderivative of 1 over x is going to be ln of absolute value of x. So that could be classified as a power rule. So in power rule, we have integral of x to the n dx is going to be equal to x to the n plus 1 over n plus 1 plus a constant c, right? Now it works perfectly, except when n equal to -1. When n equal to -1, we divide by 0. Of course, we cannot divide by 0. So notice that is good, but x cannot equal to 0. By that I mean n is not equal to 0. N is not equal to -1. Sorry. Because n equal to -1, 0 at the denominator, undefined. So we cannot do that if n is equal to -1. But when n equal to -1, it is the same as 1 over x dx. And now if it is -1, it is ln of absolute value of x plus c. Now we complete the power rule. We can take x raised to any power. If it is raised to the power of -1, it is ln of absolute value of x plus c. Any other power, we can use that power rule, right? So that complete the power rule. So derivative 1 over x, or same thing as x to -1, is ln of absolute value of x plus c. So that is the rule of the integral. Right, now we'll take a look at this. So we have x squared over -x cubed minus 5. So it doesn't look like something we can integrate right away. Usually if we cannot integrate right away, we use substitution. So what do we substitute? What do we let u equal to? Well, in this case we have look like we will let u equal to the denominator, because if we let u equal to the denominator, if u is equal to x -x cubed minus 5, the derivative of x cubed is x squared, which resembling the rest of the problem, which could be simplified. So whatever we let equal to u, take the derivative, and the derivative should cancel with what's left of the problem, which is x squared. So now, substitution, let u be -x cubed, -5. Now we take the derivative and solve for the x. So the derivative is -3x squared. Move the dx over. And then divide by -3x squared. And that gives us dx. So we have u and we have dx. And that's ready for substitution. We have x squared on the top, stay the same. The bottom is going to be u. And dx is du over -3x squared. As mentioned before, whatever the derivative should cancel with what's left of the problem. So x squared and x squared here cancel out. -1 over 3, -3 at the bottom. I move it outside, but it will stay at the bottom. And we will have 1 on the top, just to have the fraction. And then we have 1 over u du. So negative 1 over 3 1 over u. The integral of that is ln of absolute value of u plus c. Yeah, that's the properties of, the integral of reciprocal function. Right, and finally it's easy. U is negative x cubed, negative minus 5. So just have negative 1/3 ln absolute value of negative x cubed minus 5. If we know for sure the inside the parentheses can only be positive, so we just keep the parentheses, but leave the absolute values if there is a chance for that to be negative. So we need absolute values there. Right, so simple now. The reciprocal function is the integral of that is ln. Right. Now we do the same thing here. Again, we have this. If we let u equal the denominator, the top, u equal to the denominator, the derivative of that is 2x. The x there will cancel with the x on top. So that's a good substitution. Right. So let u be x squared plus 9. Right. We take the derivative and to solve for the x. The derivative is 2x. Move the dx over. And then divide by the 2x. The proper substitution, we need to have dx and we need to have u, which we do have. Now change the limit. Originally we have x equal to 0 to x equal to 4. So just make a table. Go from 0 to 4. When x equal to 0, put 0 here, 0 squared plus 9. 9. When x equal to 4, 4 squared plus 9, 16 and 9, 25. Right? Right. So with that, we can substitute back into our problem. Original problem becomes, now the limit will change. Instead of x go from 0 to 4, we have u go from 9 to 25. X still on top. X squared plus 9, that is u, right? Dx du over 2x. If it works out perfectly, all the x cancel out, and we do have that. The 2 move outside, stay at the bottom. And then we have from 9 to 25. Yeah. If we know for sure the limit is for u, just going to leave 9 to 25. 1 over u du. That gives us 1/2. 1 over u reciprocal is ln of absolute values of u. That goes from 9 to 25. Right. The rest is easy. Put 25 in and put 9 in and subtract. That is fundamental theorem of calculus. Now, ln of absolute value of 25 is still 25. So this is where we know it's positive. We just drop the absolute values. So we just say 1/2 ln of 25 minus 1/2 ln of 9. Right, that is perfect answer. Even though we can simplify that, but usually if it is definite integral, I should check when we have the limit. Math, do that. I go from 0 to 4. Fraction here, x over x squared plus 4, x squared plus 9, dx. And is that equal to 0.5 ln of 25 minus 0.5, 0.5 ln of 9? Yes, they're the same, right? Of course, so that's only this answer works. However, we can simplify this. What we can simplify is this 25 and 9. Those are perfect square, right? By the way, let me be clear that this is good enough. Now what we can do is the 5 square for 25 and 3 square for 9. Can take the power outside. One half 2 ln of 5 minus 1/2 2 ln of 3. 2 cancel out. ln of 5 minus ln of 3. And ln of, different of the ln, we can write that as ln of 5 over 3. So the properties here is ln of m minus ln of n is ln of m over n. Now if we type the natural log of 5 over 3, of course we also have the same thing. So yeah, we can stop here or any of those steps. Yeah. So usually the calculus is not that difficult. We have the derivative of the natural log function, and then we have an integral of 1 over x, the reciprocal function. But knowing the little things like in algebra, we can simplify our problem and help us simplify the problem before we do it or after we integrate. Right. Now, more sample. So up to this point we have the derivative of sine, the integral of sine, integral of cosine, but we don't know the integral of tangent. Remember, we don't know it yet. What we know is integral of secant square is tangent, because the derivative of tangent is equal to secant square. That's we know. We don't know the integral of tangent. So we need to prove it. It's not that difficult. Very fundamental tangent. We will write as sine x over cosine of x, because when we write like that, sine x and cosine x, we have the derivative and integral. Now, just similar to the last problem, what we do is we take u to be the denominator, and then we take derivative. Negative sine x, and move the dx over and then divide by negative sine x. substitution, we just have u and then dx. Right. We can continue. Sin x on the top. At the bottom, cosine of x we let equal to u. And then dx, which is du over negative sin x. Sin x and sin x cancel out this negative sign. Bring it outside of the integral. It is at the bottom. But divide by negative or multiply by negative is still negative. One over u du. Negative. 1 over u. 1 over u, because it's ln of absolute values of u plus c. And that gives us negative ln of u is cosine of x. So that's perfectly what we have. And because this is good enough. However, if you look at the back of the book or in the formula that I post in the final exam folder, this is not it. But be clear, this is good enough because we do have the integral. Right. Now what we can do is take care of the negative. So that gives us ln of cosine of x to negative 1 plus c. Of course, the properties ln of m over p equal to p ln of m. And we can check, so let's say we have x to negative 1 power. That is the same as x, 1 over absolute value of x. Right? And of course that is the same as ln of 1 over cosine of x. Yeah, so 1 over absolute value of cosine of x, 1 is positive, so we can bring the whole thing inside the absolute values, and that gives us ln of 1 over cosine is secant. And if you look in the online or whatever, the integral of tangent, they're going to give you this form instead. So this is the integral of ln of tangent of x. Right. Now how about secant? Well, secant is a little more difficult, simply because if we write secant, it's easy, of course, 1 over cosine of x. However, if we draw like that, we let u equal to cosine of x. The derivative is du over negative sin x. There's nothing to simplify. When we take the derivative of cosine, it doesn't cancel. It will stay there. So that is the problem. So writing secant as 1 over x, 1 over cosine of x doesn't help because substitution will not work. So if we do that, and then u equal to cosine of x, and dx is du over negative sin x. So we have this situation where the sin x here does not cancel with anything, and that is the big problem. So we cannot do it this way. What we do instead is this little trick, and of course I don't expect you to come up with this by yourself. But this could be classified as a classic problem where we just have a classic solution. So what we do is we multiply the top by secant of x plus tangent of x. Then you may ask, why do we do that? Well, my answer is because when we do that, it works. But because that's not the very best answer. But I suspect we just when we look at the integration problem like this, we try to, if we cannot come up with it, just guess. Just try to take the derivative of a bunch of functions and try to come up with secant. Because a derivative and antiderivative, they back and forth. So if we can guess the derivative, then we do that reverse order, we can get it. However, the proof, of course, if we know the answer, then we might have a way to go there, right? And that is classified into those scenarios. Now, I multiply the secant on the top. Secant times secant on the top, that gives us secant square, and then secant tangent. Right? Now you see why we multiply by secant, right? Or why do we multiply secant x plus tangent x? Because that is derivative of tangent. That is derivative of secant, which is the derivative of the denominator here. Yeah. So this little trick helps us to, with the substitution problem, work out perfectly. So what we do is let u be the denominator. Take derivative. Derivative of secant is secant tangent. Derivative of tangent is secant square. Move the dx. And then divide by the parentheses. So we have dx. Now let's substitute back into our problem. Secant square, trying to write small, secant x, tangent x, over, that is u, and du is this. I mean dx is that. Secant x, tangent x, plus secant square. Now it conveniently cancel out. Just have 1 over u du. Yeah. So even though we have to do this trick, but when that work out, but cancel out, we just have 1 over u du, which is the integral of that is ln of absolute of u plus c, and u is secant x plus tangent x. Right. That is the integral of secant. Now put all of them together, we have the integral of trigonometric function as follows. Integral of sin x is negative cosine x plus c. integral of cosine is sine x plus c. This is easy. We can always check derivative of sine is cosine, derivative of cosine. But to get rid of that negative, we put an extra negative there. Right, because always we can take derivative to check it. Integral of tangent, we have that. And the cofunction, of course, we can write as negative. Try to write small here. Cosecant. However, if it is negative, that certainly works. I mean, we just go from the function to cofunction and throw the negative in. Right? But the negative here, take inside, so we have ln of ln of cosecant x to negative 1 plus c, and negative 1 is the reciprocal power, 1 over cosecant, and 1 over cosecant is sine, so this is equivalent to just ln of sine x plus c. Right? Integral of secant, we did that. And integral of cosecant, secant is that, cosecant is negative ln of cosecant x plus cotangent x. However, there's a more to it. Usually they try to get rid of the negative too. Try to this negative sign. So we take it inside, and we have ln of cosecant x plus cotangent x to negative 1 power. Negative 1 power is the reciprocal function. And I said, what is the metric here? Can we simplify that? And the answer is yes, but not obvious. Not obvious. What we do here when we simplify, I will multiply by the conjugate. Cosecant x minus cotangent x. And we say, how did that simplify? Well, you see. Right. Of course, the top will be just cosecant minus cotangent. The bottom, though, cosecant times cosecant is cosecant square. Cosecant cotangent, negative cosecant cotangent plus cosecant cotangent, those cancel out, and then we minus cotangent square. Now, notice that cosecant square is equal to cotangent square plus 1. So cosecant square minus cotangent square, this is just 1. So we have cosecant minus cotangent. That's all we have. Cosecant x minus cotangent x plus c. Yeah. So you might see the integral of this in the back of the book. It's just ln of cosecant x minus cotangent x plus c. So without that negative. Of course, if we take that negative and turn to a plus, that's not obvious at all. We have to do all of this to get to that step. but that's only the integral of trigonometric function. Right, so we have the first part of the section where we have the log, derivative and integral, derivative of the natural log and exponential of, and the integral of the reciprocal function. Now we go to the second part of it, natural exponential function. Right. Now we define E, the natural base. Of course, that is the second most common constant. Of course, the first one being pi 3.14 something. E is that. And we define the exponential function. And we have the properties that exponential function and logarithmic function, since they are inverse of each other, the graph will be symmetric on the line y equal to x. So this is the graph of y equal to ln of x. We will be symmetric to the line, symmetric with the graph of the function is exponential of x. And then e to the x. Of course, properties of inverse function. The graph of the function and the inverse is symmetric on the line y equal to x. So this is the graph of e to the x. And the domain and range also interchange. Here for the ln of x, domain is x will be greater than 0. Or I should say that in the interval 0 to infinity, and the range all real numbers. So that is for the ln of x. Exponential function, since they are inverse of each other, we switch or flipped. The domain therefore will be negative infinity to infinity, and the range 0 to infinity. So that's what we have. Now with that, of course, we focus on, of course, the calculus of it. But before that, knowing these properties will help us in doing the calculus part. But first, we have this properties. This is because ln of x and e to the x are inverse of each other. So that's why we have this. This is properties of inverse. Since exponential function and are inverse of each other, right? And then we have these properties. Multiply two things with the same base, we add the exponent. Of course, that formula is a big typo there, sorry. It's not right. So that should be e to the x over e to the y. Divide two things with the same base, with the same basis, we subtract the exponent. And then power, the power, we combine the powers. Right. How do we simplify this? First of all, e and ln being inverse of each other, so that just cancel out, and that's just 2x. E and ln cancel out, this x. Now this is a little bit different because we have a product here, so they don't cancel out, ln and e, don't do that. First, we have a product here, right? So that we can split. And only then ln and e cancel out. Yeah, ln of the product is the sum of the ln. Right, now go to the calculus of the exponential function. This is the easiest one. The derivative of e to the x is the same, e to the x. So of course the integral of e to the x is also e to the x plus the constant c. So this is the only function of that kind of derivative is the same as a function. All right. Now, just need to distinguish the case when we have the exponential function or we have the power. So when we use these rules or we use the power rule. So let's look at this example. Have y equal to e to the 2x and minus 3x to the e. So notice that this we use the power rule and this is exponential rule. Put the parentheses around 2x so we can use the chain rule. So derivative e to something, then we have derivative of that. And the next derivative of x to the e, well, e is the constant, right? If it is constant, it is just the power rule. Okay, then we have 2x there, 2x here. So e to the 2x, derivative of 2x is 2 minus 3e x e to minus 1, x to the e minus 1. The 2 just bring in front so we don't need the parentheses here. Minus 3e x to the e minus 1. So that's what we have. Right. So exponential function is one of the easiest functions to differentiate. Right. Next, we have this. Once again, this is an exponential function, e raised to some power, so we just have that. So derivative is the chain rule. Derivative of e to something is the same, e to something, and then derivative of the exponent just happen to be negative 2t squared plus 1, negative 2t squared plus 1. All right. E to negative 2t squared plus 1. And derivative of negative 2t squared plus 1 is negative 4t. And we can take that in front. E to negative 2t squared plus 1. So that's what we have. And that's all we have. Right. Next. We have this, of course, obviously is the quotient rule, right? So u equal to e to the t. Derivative is the same thing. That's the easiest function to differentiate. Now if v is that, now this of course is also easy to differentiate. We can just group that and use the chain rule. going to be e to something, and then derivative of that. Derivative of -1 is 0, so we don't even have anything there. So derivative of 2t is 2. I just put 2 in front. Because we did do that, right? E to the 2x is 2e to 2x. Yeah. And then the quotient rule. U prime v minus uv prime over v square. So u prime e to the t v e to the 2t minus 1. Subtract u v prime over v square. Multiply this out, e to the t times e to the 2t. When we multiply them, we combine the exponents. The bases are the same, combine the exponent t plus 2t, so e to the 3t. Yeah. And then e to the t minus 1 times minus 1, just e to the t. And same thing here, that minus 2, e to the 3t. So that gives us e to the 3t minus that, so we have negative e to the 3t, negative e to the t. At the bottom, e to the 2t minus 1 square. Yeah, just leave the answer in this form. Yeah, because we're not going to be able to simplify that. Right, so quotient rule. Right. Right. Now, find the derivative of this. Well, you say that's the quotient rule, right? And on the top we have the product rule, but that looks like a mess. Because the product rule, quotient rule, and then the square root, that makes things a lot more complicated. Right. So is there a better way to do this? And it says yes, but not directly. So what we do here, when we have such a complicated function, we can just go ahead and take ln on both sides, because we have a lot of the properties of the ln that can simplify this expression on the right hand side. So we'll take the ln on both sides. I will rewrite, by the way, this is to the 4th power and then the square root, not the 4th root of 2x minus 1. So I say 2x minus 1, square root is 1/2, x squared plus 4. The reason we do that, because here we have a product and we have the quotient. If it is the product, we can turn that into a sum. If it is a quotient, we can turn that into a difference. And if it is a power, we can take the constant outside, take the power outside. Right, so we do that. First, there's a quotient, so I will split. So there's no calculus here yet. And then subtract, because that is a quotient. Right, still no calculus yet. There's a product, turn into a sum. And finally, can take the power, move outside. Same thing here, right? That is right. 2x minus 1 ln of x squared plus 4. Right. That simplifies a lot. If we have to take the derivative of the right hand side, it will be easy. Much easier than to deal with that directly. Now we take the derivative on both sides. So we say differentiate with respect to x on both sides. And here we have y, so that we have to use implicit differentiation. So differentiate with respect to x on both sides. On the left side, we have, put the parentheses there, derivative of ln is what? Reciprocal function, right? 1 over parentheses, derivative of the parentheses. Yeah, most of them like that. And put the parentheses here. It will be 4, 1 over the parentheses, prime. Same thing here. Plus 1/2, 1 over parentheses, prime. Minus, same thing here. Right, now just going to put y here. X cubed minus 1 2x minus 1 x squared plus 4 and then we have the y at the bottom. We can multiply that to the right hand side, multiply y on both sides, so we have y prime. Let's simplify this. 4 times 1 over x cubed minus 1. Derivative of that is 3x squared plus 1/2 times 1 over 2x minus 1. And derivative of this 2 minus 1 over x squared plus 4. Derivative of x squared plus 4 is 2x. Did we miss anything? Yes, we did. Remember, we multiply y on both sides, right? To cancel the y at the bottom here. So we just multiply everything by y. And what is y? Well, would be that. Yeah, so it's the, even though the derivative is easy to do, but at the end we're just going to write all of that back in here for y. We can simplify a little bit here though. 12 x squared over x cubed minus 1. 2 and 2 cancel out. Plus 1 over 2x minus 1. And then 2x over x squared plus 4. All of that times y, which is the original one. So I'm just going to x squared plus 4 at the bottom. Sorry, run out of space, but you get the idea. Here we have x cubed minus 1 to the 4th square of 2x minus 1. Yeah. Even though this is a lot, but it's not that difficult. We can, the thing is when we take LN on both sides, we can break that up into a bunch of little logs and differentiate these little logs. It's not that bad. Right, now find the derivative of x to the x, and then we say, how do we do that? Is that a power rule or is that exponential rule? What happens if we have x on both the bases and on the exponent? Well, we cannot use either of them. I'm not going to finish the problem, just get used to start. We also take LN on both sides in this case. That allows us to bring the x outside. We can take the derivative of that, right? Product rule. Derivative of that, implicit differentiation, and solve for y prime, and suddenly we can do that. Right. I'll let you do it. I'm not gonna do that. Now let's focus on the integral. So what we have is the integral of e to the x is the same thing as e to the x, right? Do we have any integral of that? No. Oh, not much. Right, so what do we do here? So 5 plus e to the x. Look like we have the reciprocal function, something divided by it. So we should let u equal to the denominator. If u equal to 5 plus e to the x, the derivative of that is e to the x, which cancel with this one. So we let u be 5 plus e to the x. So derivative is e to the x is e to the x multiplied e to the x over, and then divide e to the x. We have du over e to the x dx. And then substitute back into our problem. E to the x stay there. 5 plus e to the x, that is u, and dx is du over e to the x. Works out perfectly because there's no more x. Just have 1 over u du, and integral of that is ln of absolute value of u plus c. U is 5 plus e to the x plus c. Now, remember, did we say anything about the domain and range of exponential function? Yeah. Sorry. This. The range of exponential function look like that, so it can only be positive. So if e to the x is already positive, plus 5 is even more positive, but still just positive, right? So we know this is positive, plus 5 is positive. Now if ln of the absolute values of a positive number, we don't even need to do that. So this is 5 plus e to the x, just a parenthesis, because it's guaranteed to be positive. Right, so that's what we have. Right, next, what can we do? Sine x times e to the 2 cosine x. That look like substitution again, because we cannot integrate directly. So in count 1, when we cannot integrate directly, that's usually just a substitution. Unless there's some trick to it. But so what do we let u equal to? So the key here is we have both sine, cosine. Derivative of sine is cosine, right? So we should let u equal to either sine or cosine. If we let u equal to this sine x, derivative of that is cosine x. Doesn't look like it will cancel with this cosine x. That might be a problem. So if we let u equal to cosine x, derivative of cosine is negative sine. That sine x will cancel with this sine x. So in this case, it will be better if we let u equal to the exponent. To cosine x. Then we take derivative. It's negative 2 sine x. Move the dx over and divide by the negative 2 sine x. So that is the x. So sine x, and then e to the u. Dx is du over negative 2 sine x. Cancel out the sine x. Negative 2 is constant. Take it outside. Would still stay at the bottom. We have e to the u du. Integral of that is just the same thing. And finally, u is 2 cosine x. We substitute it back in. That's what we have. Right. Yeah, I realized that all of this example, we only have one example of the integral of e to the x. So in that case, that's the only one we have. So let's look at one more example. Let's do this. X x over e to the x squared dx. What is, of course, if we let u equal to the denominator, derivative of that is not simplified with this x. So if we let u equal to x squared, derivative of that is 2x, which cancel with this x. So that certainly helps, right? So let's start with that. Let u equal to x squared. Yeah. Then we just need one more example to deal with exponential function. U equal to x squared. Right? So that certainly works. It could be even better. If we just move this to the top, become negative x squared. Because if this is the case, the substitution would be a lot better. U equal to negative x squared, and then we take derivative. Will be negative 2x move to dx divided by the negative 2x. So we have x e to the u dx is du over 2x negative 2x. X is cancelled out, negative 2, bring on the outside. Still stay at the bottom though. E to the u du, which the rest is easy, right? So negative 1/2 e to the negative x squared plus c. Right. So even though when we have the exponential at the bottom, try to bring that to the top and change to negative. That certainly help. But I just want to do one more example when we have the integral of exponential function like this. Right. Right. So with that, I stop the section here. As always, thank you for watching. See you in another video in Calculus 1.